Welcome to Pre-Calculus. We begin, of course, with Chapter 4, Section 5. Here are our objectives for this section. And the objectives kind of revolve around these two: finding real zeros of a polynomial function, solve polynomial equations. Those are the ones that are the center of this section. In this video, we will start building toward that by talking about the remainder and factor theorems. We begin with the division algorithm, and this is not a big surprise. This is something you know, even though it looks crazy. Basically, it says that if you do a division, that you have a quotient and you put the remainder over the divisor. Remainder over the divisor, so that a function which is a dividend is quotient times remainder. Quotient times divisor plus remainder. So let's say our f here, let's just make a very simple example to illustrate that you already know the division algorithm. F of x, let's just say it's 302. And g of x is 8. Well, what is that? 8 doesn't go into 3, 8 goes into 33 times. Multiply, you have 24. Subtract, you have 6. Bring down the 2. And 8 goes into 62 7 times. 7 times 8 are 56. And subtract, and you have a 6. Well, what do we have here? We have that the 302 equals a quotient 37 times the divisor, which is 8, plus a remainder, which is 6. And that's actually true. 56 plus 240, that's 296, plus 6, or 302. And so this division algorithm, it's not anything that is way out in space. It's something we understand. Important theorem, remainder theorem. Let f be a polynomial function. If f of x is divided by x minus c, the remainder is f of c. So our theorem here is there's a condition, assumption that f is a polynomial function, and then there's a hypothesis, f of x is divided by x minus c, and a conclusion that the remainder is f of c. How would we establish this? Well, let's think about the division algorithm. In our hypothesis, f of x is divided by x minus c. So this g of x here is x minus c. X minus c. And the remainder is f of c. So as we update the other version of the division algorithm, they're equivalent, right? Because if you take the first one and you just multiply through by g of x, then you get the second one. Because then you cancel the g of x on the left side and cancel the g of x for the second add-in on the right side. Well, for g of x equal to x minus c, we have f of x equal to q of x, x minus c, plus r of x. Now, I want to remember this version this stage here in our demonstration that the division algorithm kind of entails the remainder theorem. Well, going back to the remainder theorem and our hypothesis there, or the conclusion now, the remainder is f of c. The remainder is f of c. So if we look at this red equation down here and ask, well, what is f of c? F of c is q of c, c minus c, plus r of c. Well, c minus c is, of course, 0, so we're zeroing out that factor. But of course, that's multiplied by q of c, so all of this is going to get blown up. And what we're left with is that the remainder, is f of c. And that is the conclusion of the remainder theorem. Let f be a polynomial function. Then x minus c is a factor of f of x if and only if f of c equals 0, the very important factor theorem. Okay, so x minus c is a factor of f of x if and only if f of c equals 0. Now let's remember that equation to which I drew your attention earlier. That was before we asked about f of c, but when we were talking about the hypothesis of the remainder theorem, that f of x is divided by x minus c. Then we wrote this equation, f of x equals q of x. We said g of x was x minus c plus r of x. Okay, and we put a nice, actually it wasn't very well drawn. Neither is this one, but looks a little bit better. And so now let's think about this equation in connection with this factor theorem that we're trying to establish. X minus c is a factor of f of x if and only if f of c equals 0. Well, what is f of c? F of c is q of c. Oh, I'm doing remainder theorem again. Okay. X minus c is a factor of f of x if and only if f of c equals 0. Okay, so now let's say that f of c does equal 0. Then Well, according to the remainder theorem, the remainder is f of c. Okay, according to the remainder theorem, the remainder is f of c. And by hypothesis, f of c equals 0. Now, why do you call it the hypothesis? It's at the end. That should be the conclusion. Well, we'll talk a little bit about that. But f of c equals 0. Now, if f of c is equal to 0, then you've kind of blown up this last term here. And so this part's gone. And we have that f of x equals q of x, x minus c. And so x minus c is a factor. You can see that x minus c can be multiplied by something to make the f of x. And so x minus c is a factor of f of x. Now, as we were just saying, when we're talking about hypothesis conclusion, factor theorem actually consists of two separate statements. F of c, if f of c equals 0, then x minus c is a factor of f of x. And that's what we established last time. We started with the second statement, f of c equals 0, and then demonstrated the first part. And then the other statement that is part of the conjunction, which is the factor theorem, is that if x minus c is a factor of f of x, then f of c equals 0. So it's two things if you have an if and only if in the statement, okay? Because if you have an if and only if, you're really saying two things. You're saying, if you say P if and only if Q, P if and only if Q. That's what we're saying in the factor theorem, okay? P if and only if Q. Well, this is saying two things. This is saying if you look at the only if you look at the only if, this says P only if Q. P only if Q. And really what this means is if P, then Q. If P, then Q. Okay. Which is actually the second one here. If P, that is, if x minus c is a factor of f of x, then Q, f of c equals 0. But now, if you look at the if part, then what we have is P if Q. P if Q. Which is the same thing as if Q, then P. If Q, then P. Okay, so pretty advanced stuff here for the very first section. If P, then Q, which of course is the first part. So if you see an if and only if, just remember that it's a biconditional. The conditional goes both ways. Using the factor theorem. Use the factor theorem to determine whether the function... Oh, I wanted to say one more thing before we get to this problem about the factor theorem, which I have in the upper right of this slide. What does this part say, really? F of c equals 0. That means that c is a 0 of f of x. Right? If you think about what a 0 is, c is a 0 because f of c equals 0. 0 is the number that c is the number that zeroes out f, that function. So if you were to graph f of x, it would have an x-intercept at c. C is a 0. Okay, very theoretical this first video, so sorry about that. The future ones won't be so much. And this problem will not be so theoretical. It's pretty straightforward to do. Use the factor theorem to determine whether this function, a polynomial function, by assumption, has the factor x minus 1. Now, in this case, c is 1. Okay. And so, right, the c is the same thing as the 1. If you look at this, the c is the 1. And so that is going to be true if f of 1 equals 0. So that's the question we're going to be asking about A. Is f of 1 equal to 0? And about B, what is C? Well, C is actually negative 2, right? Because if we think about x minus c, c is always the number that is subtracted from x. And what is subtracted from x here is negative 2. So let's just be clear that c equals negative 2. Well, let us determine whether these things are the case. Whether x minus 1 is a factor of this polynomial function f of x, and also part B, whether x plus 2 is a factor. Well, to determine whether x minus 1 is a factor, we will just see whether f of 1 would be 0, and then that'll tell us yes or no the answer to part A. Okay, so we go ahead and find f of 1, as we said was our strategy, and we want to know, is that 0? And so we plug it in. Okay, we plug it into f of x, and so since f of x was 2 times the cube of x minus the square of x plus 2x minus 3, we plug 1 into that, and what do we have? We have 2 times 1, so 2 minus 1 plus 2 minus 3. That is not, that is 0 actually, because you have 1 plus 2 minus 3, or 3 minus 3, which is 0. And so the answer is yes, x minus 1 is a factor of f of x. Of course, we would write all that out in words. To test the factor x plus 2, write it in the form x minus c. And as we were saying, the c is negative 2. to find the value of negative 2. Now, we're not actually following the factor theorem here. We are going to do the division directly. And we're going to use synthetic division. So the C is the number that always goes into the loft in synthetic division, if you recall. And here we have the coefficients of f of x, because it was 2x cubed minus x squared plus 2x minus 3. Take those coefficients, bring down the first thing, multiply 2 times negative 2, 2 times negative 2, multiply, write the result here, and add. We get negative 5. Then negative 5 times the negative 2 are 10. And add to get 12. 12 times negative 2 are negative 24. And you add and we get negative 27. So remember, synthetic division was a process of multiply and add, multiply and add, multiply and add. And of course, when what we were looking for in this division was zero remainder. I'll separate quotient from remainder here. But that's not 0 right there. And so negative 27 is not 0. From the factor theorem, x plus 2 is not a factor of f of x. The division does not go evenly. We conclude with a seemingly clear theorem. A polynomial function cannot have more real zeros than its degree. How are zeros represented on a graph? As x-intercepts, right? X-intercepts. X-intercepts. And so take, for example, a fourth degree function, which is kind of like a parabola but with an extra blip in it. Well, it could have 4 zeros. Could be 1, 2, 3, 4. Could look like that, where you'd have 1, 2, 3, 1, 2, 3, 4 x-intercepts and 4 zeros. But then again, maybe it doesn't. Maybe your fourth degree function, which is like a parabola but with an extra blip in it, comes down here. There's a 0, there's a 0, but then, you know, sometimes it does that. And so maybe it only has 2 x-intercepts, 2 zeros, and so it could have 4, it could have 2, could have 3, could have none for this particular fourth degree function. A polynomial function, but what we have to say about all of that is that a polynomial function cannot have more real zeros, in this case 4, than its degree, which is 4. Now get it done for objective 1.